Introduce the boundary layer theory, the Prandtl boundary layer equations, and also the von Karman momentum balance. We're going to use these as our foundation to look at our first example, which is looking at laminar flow along a flat plate. So let's write that down. So we're going to look at laminar flow. Laminar flow along a flat plate. So this is a approximated solution using the von Karman momentum balance. So again, let's first draw a schematic describing our problem. So we have this flat plate like that. We have fluid approaching from the left with a velocity v infinite. So fluid approaches with v infinite. Again, we will define the direction along the plate as x and perpendicular to it as y. So we will expect once the fluid touches the very front of that flat plate, we would start having boundary layers forming. So we expect the boundary layers be forming, and that boundary layer will grow as the fluid is flowing downstream. Let's try to make it like that. Okay, that looks a little bit better. It's not perfectly symmetric, but passes on the message. So inside these two lines are our boundary layer. And we know that inside the boundary layer, we will have velocity gradients, which starts from 0 at the solid surface and becomes a constant once it exceeds the boundary layer, right? So you have velocity gradients like that. And so basically this height here would be our boundary layer thickness, which is a function of x. It's going to grow thicker and thicker along the x direction. And here we have the velocity profile here, v sub x, which is a function of x and y. Okay. So remember that we've just introduced the von Karman energy or the von Karman momentum balance. Let's write that down here. So the von Karman momentum balance So on the left-hand side, we have the shear stress exerted on the wall by the fluid. So it's going to be the viscosity times the partial derivative of Vx over Vy at y equals 0. And that is because after the integration from y equals 0 to y equals infinite, you do not have this term anymore at y equals infinite. So that's your left-hand side, and on the right-hand side we have two terms. The first one would be d dx times the integration from 0 to infinite times rho vx times v sub e minus vx dy plus d v sub e dx times the integration from 0 to infinite times rho v sub e minus v sub x dy. Okay, so how should we proceed from here, right? So clearly our objective here is to actually figure out the velocity profile here, so we can actually know, information about the shear stresses and information about the, the momentum fluxes, right? So again, as we've been doing continuously throughout this course, is we would try to use the physics behind it to make proper guesses of the solution, at least the form of the solution. So here we're going to do that again. We are going to make a guess of the form of the solution. So form of v sub x, which is a function of y. Okay? So our guess would be like the following. Basically, we know that v sub x of y would be a function of y within the boundary layer thickness. Once you're outside the boundary layer, there's no any y dependence anymore. It'd be a constant. Okay, so here the delta x of x would be the thickness of the boundary layer at different positions. Okay? So with that said, we can kind of guess that for, y within the boundary layer, so between 0 and delta of x, we also know that there are some boundary conditions, right? So we know that v of x at 0, which is at the surface, we have a no-slip condition equals to 0. And we also know that Vx at delta, which is at the boundary layer, at the outermost outermost part of the boundary layer, we have Vx equals to V sub e. Okay. So here we can have combining the information of, v of x should be a function of y over delta, and the fact that we have these two boundary conditions, and the fact that we would hypothesize this, a curve-like shape for our boundary layer thickness, we can kind of guess that also the key, I'm drawing the wrong thing here. And we know that typically the velocity profile is some curve, like a parabolic curve. So a reasonable first guess can be something like the following. Let's guess that v of x over v infinite would equal to some constant times y over delta minus some constant times y over delta to the third power. Okay, so this guess satisfies the two things here. The first thing is satisfied that it should be a function of y over delta. The second thing is satisfy the first boundary and the second boundary condition, right? So you can see that it satisfies both. Okay, so basically this would be a plausible guess with reasonable a bowl shape. Okay, so we see that for this particular guess, v sub x over v infinite equals to 1 for y greater than the boundary layer thickness, meaning that the potential flow regions. So maybe we should also use a black color. So this is in a similar level, right? So these two must be combined actually to describe our velocity profile. Okay, so basically this satisfies no slip condition at y equals to 0. And also importantly, there's a third condition that must be met, right? So remember that the velocity not only has to be equal to the v infinite at the boundary layer and potential flow interface, but outside the boundary layer, you should not have any variation of the velocity with respect to y. Okay, so that means that the slope at the boundary layer should be 0, or the gradient. So the second thing here is importantly, partial vx partial y should be 0 at y equals delta. So let's see if that's the case, right? If we take a derivative of this equation, we see that vx over v infinite to the first derivative equals to 2/3 times 1 over delta minus 2/3 times y over delta square. Sorry, this is, let's put it properly, so y squared, but delta cube. So this equals to what? This equals to 2/3 minus 2/3 equals to 0 when y equals to delta. So correct. Okay, so once we have a plausible guess here, and let's try to emphasize what the plausible guess has to satisfy. It has to satisfy first, it's a function of y over delta. It has to satisfy the no slip condition. It has to satisfy being equal to v sub e at delta. And also has to satisfy that at y equals to delta at the boundary layer most outer surface, it has to satisfy that it has 0 gradient with respect to y. Okay, so there's actually 3 conditions that it has to meet. And also it has a reasonable shape, the curve shape, right? So once we have this equation, this guess formulated, we can now substitute the guess into the von Karman equation. So let's do that. We're going to substitute into von Karman equation. And here we get that if we substitute that into the equation, we have the following. We have 2/3 of mu v infinite over delta equals to d dx 39 over 280 times rho v infinite squared times delta. Okay, so this is basically a separable first order ODE. Right, so just to make sure we can understand, delta is delta of x here. So now we have the solution being delta x, or delta of x, equals to the square root of 280 over 13 times the kinematic viscosity times x over v infinite. So it's roughly equals to 4.64 times the square root of the kinematic viscosity times x over v infinite. And using the delta of x, we can now obtain the velocity distribution. Which would be v sub x over v infinite equals to 2/3 times y times the square root of